Hey guys, welcome back. In the last lesson, we looked at compression. We saw the benefits of compression, and more importantly, we saw one serious drawback of compression, which is when a file is compressed, Hadoop processes the file as a whole with one mapper instead of processing the file in a distributed way with each input split processed by an individual mapper. The reason for this is because of the way compressed file is structured. With a compressed file, record reader in your input format cannot seamlessly position itself from one block to the next block. We mentioned that sequence file offers a solution to this problem. But before we look at that, let's first understand what are sequence files. In this lesson, we will look at what are sequence files, structure of sequence files, compression in sequence files, creating a sequence files, and solving small files problem in Hadoop with sequence files, and finally execute a MapReduce program against a sequence file. That's a lot, so let's not wait any more time and let's get started. Sequence file is a special kind of file. When you want to read and write text values in Hadoop, you would use text files and you would use text input format and text output format. Similarly, when you want to read and write binary types into a file, you can use sequence files. Let's say you have an user object in Java with properties like first name, last name, their phone number, and addresses, etc. You would like to store the object as it is into a file. You could use sequence files for that. In short, sequence file offers an excellent structured way to store binary types. Just like you have text input format and text output format to read and write to text files, we have sequence file input format and sequence file output format to read and write from the sequence file. Let's now look at the structure of the sequence files. A sequence file is built up of records. Each record is a key value pair. So when you read and write to sequence files, you would write and read key value pairs to and from the file. You will also see sync markers and arbitrary positions in between records in a sequence file. We'll talk about the purpose of sync markers in a bit. When you are reading the sequence file, you would have to know the class type of the key and the value, and also any compression related information about the file as well. Such information are stored at the very beginning of the file in the header, which has the metadata about the sequence file. This is the high-level structure of the sequence file. Now let's look closer at the structure of the record inside the sequence file. The structure of the record varies depending on whether you chose to do compression or not. In a sequence file, you can only compress a value in the record. So whether you compress or not, the first three elements in the record will always remain the same. The first element gives you the length of the record. The second element gives you the length of the key. Both first and second element are 4 bytes in size each. The third element is the actual key in your key value pair in the record. The last element is the value, and if compression is enabled, the value will be compressed, and it is called record level compression because the value in each record in this case is compressed. You can also choose to compress multiple records together, and it is called block level compression. And it is preferred over record level compression because block level compression has the opportunity to take advantage of the similarities between records and can offer an efficient compression when compared to the record level compression. Let's look at the structure of the sequence file with block level compression. The first element, as usual, is the header, and you have sync markers between each block. First element inside the block gives you the number of records in the block. The remaining 4 elements are compressed. Second element gives you the length of the keys, and the third element contains the actual keys. Fourth element has the length of values, and finally the last element has the actual values. As you can see, all the elements here are compressed, except for the first element. So no wonder block compression is efficient and preferred over record level compression. Let's now talk about sync markers or sync points. Regular compression is awesome, but plain compressed files cannot be splitted in a MapReduce job, and hence the compressed files are processed as a whole, which is not ideal. The reason for this is because of the way compressed file is structured. With compressed files, record reader in your input format cannot seamlessly position itself from one block to the next block. Sync points or sync markers solve that problem in sequence files. It allows the record reader to synchronize with record boundary from any arbitrary position in the stream. This allows the sequence file to be splittable, and that is why sequence files are extremely popular in Hadoop environment. Because there are several advantages, right? First, sequence files allow you to store binary types, and second, they allow you to compress at the record level or at the block level. And third, and most importantly, compressed sequence files allow splitting during MapReduce execution. Okay, let's see what we have seen so far. So far, we have seen what are sequence files, structure of sequence files, compression in sequence files. Now let's look at how to write a sequence file. I have a very simple Java program which takes a file in HDFS, which is an uncompressed stock dataset, and convert that into a sequence file. The program takes in three arguments. The first argument is the location of the input dataset. The second argument is the output location where the converted sequence file will be stored. The third argument is a Boolean value which indicate whether the sequence file should be compressed or not. So this is what we're going to do. We will read one line at a time from the input dataset. The length of the line will be our key in the record, and the entire line will be recorded as the value for the record in the sequence file. Make sense? First, you need a handle to HDFS. FS data input stream gives you a handle to HDFS. Next, you need to create a sequence file writer. In the writer, you will specify the type of the key and the type of the value. Our key is the length of each line from the input dataset, right? So the type of the key will be long writable. And hence each line item is text. We'll use text as the type for the value. And here we are enabling block level compression if we are passing true as the third argument to the program. But if you like to enable record level compression, simply specify compression type.record. And when you enable compression, specify the codec as well. Here we want our file to be compressed using gzip, so we have mentioned gzip codec. Next, in this for loop, we will loop through all the files in the input folder location. For each file, we will open the file, read each line from the file. The length of the line will be recorded as the key, and the actual text from the line will be recorded as the value in the record. And it will be repeated for all the records in the file and for all the files in the folder. So in the end, when the program completes, all the records from all the files in the input folder location will be written into one sequence file. This is an interesting and widely used use case for sequence files. Let me explain. Hadoop works exceptionally well with big data sets, but it is not an efficient platform when you have a lot of small files. Meaning when you have a lot of files significantly less than the block size. Because it puts a stress on the name node. Because your name node has to maintain metadata information about a lot of small files as opposed to one big file. Also, since the files are so small, each mapper will be now processing a split which is significantly lesser than the block size of your cluster. And your job when processing a lot of small files will end up with a lot of mappers, each running against a small file for a short duration, which is not ideal, and it is an underutilization of your cluster resources. Hence, it is often best to consider a consolidation strategy of all your small files, especially when you have a lot of small files which are being processed over and over again. Let's say we have a lot of small files. How can we consolidate them? Very simple, right? We can write a small program to read each text file and write the contents from each small text file into one big text file. Sounds good, but do you see a problem with that? The problem is, if you would like to compress the contents of the big text file, you can, but your compressed file cannot be split during MapReduce execution, correct? So in real world, you would use a file format like sequence file to consolidate small files. Because if you decide to compress the file, you can do so either at the record level or at the block level and can still split the file while MapReduce processing. That is exactly what we are doing with this program. The program is looping through all the files in the input folder location and process one file at a time and consolidate the files into one big sequence file. So if someone asks you about your opinion on small files in Hadoop cluster, you can tell them that Hadoop is not an efficient platform to process lots of small files. And the best option is to use a file format like sequence file to consolidate the small files into a big data set. Now let's run this program in our cluster. I've already exported the program as a jar. So to export this program, just right click on the project and just say export jar file, click next and choose a location and hit finish. That's it. Your program or your project will be exported as a jar. And here's the command to execute the jar file. I'm using the Hadoop jar command here instead of the just plain jar to execute this jar that we just created, because using Hadoop jar would conveniently include all the necessary Hadoop jars in the class path. And also you can see I'm passing 3 arguments to this program. The first argument, which is this right here, is the input location, which has the stock dataset which this program will look up and convert into a sequence file. And the second argument is the output location in HDFS, where we want to store the sequence file. And the last argument is a Boolean argument, which tells the program whether the sequence file should be compressed or not. So in this case, I'm passing true, so I'm going to compress the sequence file at the block level. So let's look up the input location first in HDFS. There you go. Our input location has one big data set, which is the stocks data set, which is about 1 GB in size. And you can choose to have a lot of small files in this location. But for this example, I have chosen to use one big data set, and we're going to read this data set and convert this data set into a compressed sequence file. So let's run this program to convert the big stocks data set into a compressed sequence file. Since you're using gzip compression, it has already loaded the gzip compressor, and it is now processing the stocks big data set from the input location, as it says right here. The number of lines written is a little over 22 million. So we have read 22 million lines from our stocks dataset, and we have created a sequence file. So now let's look at the output location where we stored the sequence file. So here's the output location. So copy that, Hadoop FSLS. So here is the sequence file. So we have taken a data set which is 1 GB in size, and we have converted that to a compressed sequence file. And the size of the compressed sequence file, it's about little over 300 MB. 1 GB to little over 300 MB. So that's pretty good, right? Okay, I've already mentioned several times now the main advantage with sequence file is that the sequence file will allow splitting even when the file is compressed. Let's see this in action. Let's run the same maximum close price MapReduce program against this sequence file and see whether the job is executed with more than one mapper. Now let's look at the MapReduce program. So here is a simple MapReduce program to process the sequence file. What changes do you think we should make to the MapReduce program to make it run against a dataset in sequence file format? All you need to do is just change 2 words in the program, and that is it. Hadoop will take care of the rest. When you specify the input format, in place of the text input format, you have to specify sequence file input format. You can output the file as text input format as well. But here we are going to output the file as sequence file output format. Now let me ask this question. We have not specified the type of the key and value in the record in our sequence file, in our MapReduce program. And also we did not mention that the sequence file that we have is compressed at the block level in the program. So how does this MapReduce program know about those information while processing the sequence file? Any guesses? Take a look at this slide. The sequence file begins with the header, and the header has the metadata information about the sequence file and will have all the information about the sequence file. So when the sequence file input format starts reading the file, it will look up the header and get all the metadata information about the file that is needed for processing. The mapper and the reducer program just remains the same. There are no changes to it. I've already exported this program into a jar, and I have copied the jar in the cluster in this location right here. Now let's execute this MapReduce program in our cluster and make sure that this MapReduce program will create multiple mappers to process the data set. Let's first delete the output location so that our MapReduce program won't fail. The output location is now deleted. Now let's execute the MapReduce program. Immediately you can see the number of splits is 3, which is a very good sign, which means this MapReduce program is going to use 3 mappers to process the sequence file. There you go, the MapReduce program is now completed successfully. Let's review the execution of the MapReduce job. So let's copy this application URL. Here's the application. As you can see, the number of maps used here is 3, which tells us that even though our sequence file is compressed, Hadoop was still able to split the sequence file and process the file with multiple mappers, which wasn't the case with just plain compressed files. And this is exactly what we wanted. Now we have executed a MapReduce program against a sequence file, and we have also verified that even though the sequence file is compressed, our MapReduce program was able to split the file and process each split with an individual mapper. Now let's look at the actual output. So let me do the listing on the output directory. So there you go, here's the output, and this is actually a sequence file. Let's try to open this file with hdfs cat command. Since our output file is a sequence file, if you open the file will not be in a readable format because we are writing binary types into the file. So when you open a sequence file, instead of using fs-cat, use fs-text. So let's execute this command. The -text flag is going to read the sequence file and is going to display the output in a readable format. So here's our output. That is it, guys. We have learned a lot in this lesson. So let's summarize what we learned. We learned what are sequence files. We also know the structure of sequence files. And we created a sequence file with block level compression. We also saw a use case to solve small files problem in Hadoop with sequence file. And finally, we executed a MapReduce program against a sequence file. With that, let's wrap this lesson. See you in the next lesson.